If a UPS system is repeatedly switching between battery and online modes when powered by a generator, there are several potential causes to investigate. Firstly, frequency discrepancy could be the culprit. The UPS system is likely sensitive to frequency variations. In this case, a generator frequency of 63 Hz is outside the acceptable range for most UPS systems, which typically require a frequency of 60 Hz plus or minus 2 Hz. The solution here is to install a frequency converter to regulate the generator's frequency to the required 60 Hz plus or minus 2 Hz range. Secondly, voltage variation may be a problem. The UPS system might not tolerate the voltage variation from the generator. The generator voltage of 125 volts line to neutral and 250 volts line to line is slightly different than the nominal 120 volts and 240 volts typically needed for residential applications. To fix this, adjust the generator's voltage regulator to output the correct voltage of 120 volts line to neutral and 240 volts line to line. Thirdly, harmonics could be a contributing factor. Generators can introduce harmonics into the power supply, which can interfere with sensitive electronics. In this instance, install a harmonic filter between the generator and the UPS system to mitigate harmonic distortion. Fourthly, wiring issues can create problems. Make sure that the wiring connections between the generator, transfer switch, and UPS system are correct and secure. Loose or incorrect connections can cause voltage drops or ground faults. It's important to check all wiring connections and tighten any loose terminals. Fifthly, UPS sensitivity settings could be a factor. The UPS system may have sensitivity settings that need adjustment to properly accommodate the generator power. Contact the UPS manufacturer for assistance and guidance on adjusting the sensitivity settings to match the generator's output. Sixthly, grounding is very important. Ensure that the generator, transfer switch, and UPS system are properly grounded. Improper grounding can cause electrical noise and interfere with the UPS system's operation. Verify that all grounding connections are secure and meet electrical codes. Seventhly, load management is also important. The generator's output might not be sufficient to power all the equipment connected to the UPS system. Reduce the load on the UPS system by disconnecting non-essential equipment or installing a load shedder to automatically disconnect non-critical loads when the generator starts. An isolation transformer can help to further reduce interference, but may not be necessary if the solutions already described resolve the problem. Regular generator maintenance is essential to prevent potential problems. Make sure that the generator is regularly serviced and maintained. In summary, to address the UPS system's issues with generator power, firstly, check and correct the generator's frequency. Secondly, adjust the generator's voltage to match the required levels. Thirdly, install a harmonic filter to reduce interference. Fourthly, verify and secure all wiring connections. Fifthly, adjust the UPS system sensitivity settings. Sixthly, ensure proper grounding for all components. Seventhly, manage the load and the generator. Regular maintenance is critical for the generator. By systematically addressing these potential issues, you can improve the compatibility between the generator and UPS system. This in turn will provide reliable backup power for the IT department. When dealing with electrical systems, it is essential to adhere to safety precautions and consult with qualified electricians or technicians when needed. The NEC, or National Electrical Code, serves as a comprehensive guide for electrical installations. Article 712 addresses the generator set location and lists some considerations. The location has to be suitable for the environmental conditions, including being away from hazardous locations as in 500. The generator sets have to be installed in a separate room. If it is inside a building, it needs to be separated by a 2-hour fire resistance rated enclosure. Generator sets can be installed on the roof of the building. Section 700.12b5 covers protection against equipment failure. The emergency power system should have overcurrent protection. This is sized to protect the generator from overload and short-circuit conditions. Proper coordination ensures selective tripping, isolating the fault while allowing other parts of the system to continue operating. NEC Table 220.42 can be used to determine the demand factor for the feeder conductors for general lighting and other occupancies. Look at Table 220.42, which provides demand factors for general lighting in various occupancies other than dwelling units and hospitals. Note the footnote at the bottom. These demand factors are permitted to be applied to the general lighting load. Table 220.12 lists the general lighting loads by occupancy. For example, an office building has a unit load of 3.5 volt amps per square foot. A bank has a unit load of 3.5 volt amps per square foot, and a school is at 3 volt amps per square foot. If the building has a fire alarm system with its own dedicated circuit, it should be calculated separately. In most cases, it is a very small load. In addition to lighting, there are receptacle circuits to consider. The NEC requires specific spacing requirements for receptacles in various locations. For example, in office spaces, receptacles must be installed no further than 12 feet apart. For general use receptacles, the NEC typically requires an allowance of 180 volt amps per receptacle outlet. This allowance covers the anticipated load from typical office equipment and devices. To calculate the total receptacle load, multiply the number of receptacles by 180 volt amps. For example, if there are 50 receptacles, the load would be 50 times 180 volt amps, which equals 9000 volt amps or 9 volt amps. For any large or specific equipment such as HVAC systems, servers, or specialized machinery, obtain the actual power requirements from the equipment's nameplate or manufacturer's specifications. This will provide the most accurate load calculation for these devices. Add all the individual loads together, including lighting, receptacle circuits, dedicated equipment, and any other electrical load served by the generator. This will give you the total connected load in volt amps or kilowatts. Apply demand factors to the connected load to account for the fact that not all loads will operate at their maximum simultaneously. Demand factors vary depending on the type of occupancy and the nature of the loads. Consult the NEC for appropriate demand factors for different applications. After applying demand factors, you will arrive at the estimated maximum demand load that the generator must supply. This value is crucial for selecting an appropriately sized generator. Consider future expansion when sizing the generator to accommodate future growth or additional equipment. It is generally recommended to add a safety margin of 20 to 25% to the calculated demand load to account for uncertainties and potential increases in power demand. The generator's power factor also affects the sizing. Generators are typically rated in kilovolt amps or kilowatts at a specific power factor, such as 0.8. Ensure that the generator's kilowatt rating is sufficient to supply the calculated demand load. Consider factors such as altitude and ambient temperature, which can affect the generator's output capacity. Directing factors may be necessary to account for these environmental conditions. Finally, select a generator with a kilowatt rating that meets or exceeds the calculated demand load, including safety margins and directing factors. Consult with a qualified electrical engineer or generator specialist to ensure proper sizing and selection. Regular maintenance is essential for the reliable operation of the generator. This includes periodic inspections, testing, and servicing of the generator, transfer switch, and associated components. To perform voltage drop calculations, firstly, determine the allowable voltage drop. The NEC recommends limiting voltage drop to no more than 3% for feeders and 5% for branch circuits to the furthest outlet. Secondly, identify the conductor length. Measure the one-way distance from the power source, such as the generator, to the load. For a three-phase system, use the line-to-line voltage, which is 208 volts, 240 volts, or 480 volts, depending on the system configuration. Thirdly, determine the conductor impedance. Obtain the impedance values for the conductor from the manufacturer's data or the NEC tables. Consider the conductor material, size, and insulation type. Use the appropriate formula to calculate the voltage drop. The formula varies depending on whether the system is single-phase or three-phase. For a single-phase system, the voltage drop is typically calculated as voltage drop equals 2 times the current times the length times the impedance divided by 1000. For a three-phase system, the voltage drop is calculated as voltage drop equals the square root of 3 times the current times the length times the impedance divided by 1000. Ensure consistent units, such as amps for current, feet for length, and ohms per 1000 feet for impedance. For example, suppose a 240 volt single-phase circuit has a load current of 20 amps, a conductor length of 100 feet, and an impedance of 0.2 ohms per foot. The voltage drop would be 2 times 20 amps times 100 feet times 0.2 ohms per foot, which equals 8 volts. Calculate the percentage voltage drop by dividing the voltage drop by the source voltage and multiplying by 100. In the example, the percentage voltage drop would be 8 volts divided by 240 volts times 100, which equals 3.33%. If the calculated voltage drop exceeds the allowable limits, consider increasing the conductor size, reducing the conductor length, or using conductors with lower impedance. In addition to calculations, consider factors such as conductor temperature, conduit fill, and bundling, which can affect the conductor impedance and voltage drop. For complex circuits or critical applications, it may be necessary to use specialized software or consult with a qualified electrical engineer to perform detailed voltage drop analysis. Consider the ambient temperature, conductor bundling, and conduit fill. These factors affect conductor ampacity. Ambient temperature is the temperature of the environment in which the conductor is installed. Higher ambient temperatures reduce the conductor's ability to dissipate heat, decreasing its ampacity. Conductors installed in environments with high ambient temperatures must be derated according to NEC tables. The NEC provides ampacity correction factors for various ambient temperatures. Conductor bundling refers to the practice of grouping multiple conductors together in a raceway or cable. When conductors are bundled, they generate heat, which reduces their ability to dissipate heat effectively. This requires derating the conductor ampacity according to NEC tables. The NEC provides adjustment factors for different numbers of current-carrying conductors in a raceway or cable. Conduit fill refers to the percentage of the cross-sectional area of a conduit or raceway that is occupied by conductors. The NEC specifies maximum allowable conduit fill percentages to prevent overheating and ensure proper heat dissipation. Exceeding the maximum conduit fill percentage can reduce the conductor ampacity and increase the risk of insulation damage. The NEC provides tables and guidelines for determining the allowable number and size of conductors in a given conduit size. To determine the corrected conductor ampacity, firstly, obtain the base ampacity of the conductor from the NEC tables based on its size and insulation type. Secondly, determine the ambient temperature correction factor based on the actual ambient temperature in the NEC tables. Thirdly, determine the conductor bundling adjustment factor based on the number of current-carrying conductors in the raceway or cable in the NEC tables. Fourthly, apply the ambient temperature correction factor and the conductor bundling adjustment factor to the base ampacity to obtain the corrected conductor ampacity. The corrected ampacity is the maximum current that the conductor can safely carry under the given conditions. Compare the corrected ampacity with the load current to ensure that the conductor is adequately sized for the application. For example, suppose a number 12 AWGTHHN copper conductor has a base ampacity of 30 amps according to the NEC tables. The conductor is installed in an ambient temperature of 95 degrees Fahrenheit, which requires a correction factor of 0.88. There are 6 current-carrying conductors bundled together in a raceway, which requires an adjustment factor of 0.8. The corrected ampacity would be 30 amps times 0.88 times 0.8, which equals 21.12 amps. Therefore, the number 12 AWGTHHN conductor can safely carry a maximum current of 21.12 amps under these conditions. If the load current exceeds 21.12 amps, a larger conductor size would be required. Consult with a qualified electrical engineer or electrician to ensure proper conductor sizing and ampacity calculations based on specific application requirements and local electrical codes. Proper grounding and bonding are essential for electrical safety and system performance. Grounding provides a low impedance path for fault currents to return to the source, while bonding ensures electrical continuity and minimizes voltage differences between metallic parts. The NEC specifies requirements for grounding and bonding to protect people and equipment from electrical shock and fire hazards. Grounding refers to the connection of electrical equipment and systems to the earth, providing a reference point for voltage stabilization and fault current dissipation. The grounding electrode system typically consists of a ground rod, ground plate, or underground metallic water pipe connected to the building's electrical system. The grounding electrode conductor connects the grounding electrode system to the equipment grounding bus in the service panel. Bonding refers to the interconnection of metallic parts to create an electrically conductive path, minimizing voltage differences and providing a low impedance path for fault currents. Bonding conductors are used to connect metallic enclosures, raceways, equipment frames, and other non-current carrying metal parts. The main bonding jumper connects the equipment grounding bus to the neutral bus in the service panel, providing a path for fault currents to return to the source. Equipment grounding conductors provide a path for fault currents from electrical equipment back to the source, tripping the overcurrent protective device and energizing the circuit. These conductors are typically run with the circuit conductors and connected to the equipment grounding terminals. Size the grounding and bonding conductors according to the NEC tables based on the size of the overcurrent protective device protecting the circuit. Ensure that all grounding and bonding connections are secure and properly tightened to provide low impedance paths. Inspect grounding and bonding connections periodically to ensure they are intact and free from corrosion. Do not use water pipes as the sole grounding electrode. Supplement water pipes with additional grounding electrodes such as ground rods or ground plates. Proper grounding and bonding are essential for electrical safety and system performance. Consult with a qualified electrical engineer or electrician to ensure compliance with the NEC and local electrical codes. Remember to follow NEC guidelines when working with electrical systems.